Thanks
Okay.
everyone for hanging with us, and thanks for joining us this afternoon. My name is Dean Lees, and I'm the Director of Engineering at Buckley Associates. And today we have Mike Post with us to present on increasing building efficiency with airflow measurement and control. Mike is from Ebtron, and we're going to be talking primarily today about how you can use airflow measurement as a means to improve indoor air quality, but also improve building efficiency and improve the health within buildings through that indoor air quality improvement. So we'll get going here shortly. Just a few administrative items before we get going. We have quite a few people on the line here today, so everyone's going to remain muted for the duration of the session. But ultimately, this session is for you, our clients. We want you to get the most out of it that you possibly can. So if questions come up, please use the question function in the top right hand corner of GoToWebinar. You can type in your questions there. There's also the chat function as well. You can use that. Mike, we've lost your screen for some reason here.
Yeah, I got you. All right. You got
Okay.
it again?
Yep. Now that we got Mike's screen, we'll get going. So thanks for joining us today, Mike, and thanks for presenting on this topic.
Yeah. Thank you. Thanks, Dean. Appreciate that. Thank you, Buckley, for inviting me to join in this today and participate in this. I appreciate everybody that's joining in online. Thank you for being here. In cognizant of time, I've got 12:06. I know we want to try to wrap up here probably by 1 o'clock. So we'll work on that in this presentation. I think I've got it to the right amount of slides where we can do that. As for questions, I believe there's a way in the chat box to type in questions, and those will be monitored by Jessica. And if we don't have time to address each question, we'll be able to address them after the fact and then send out a report to everybody of all the questions that were asked and then what our response is to those questions. So I hope that is beneficial for everybody. So again, thank you very much. Thanks, Dean. As he said, I'm Mike Post. I'm the division manager for the East, cover from Florida to Maine, and based here in Atlanta, Georgia. So as Dean said, we're going to talk about increasing building efficiency, utilizing airflow measurement and control, and that also has a big effect on indoor air quality, and we'll discuss that. So what are some things we're going to talk about today? We're going to talk about why measure and control, various air paths within the system, not just outside air, but other areas as well. Why do we condition and ventilate in the first place? How much does it cost us to treat outside air? That kind of information. I do want to talk about the various technologies that are used for measuring airflow, because as we get into the discussion of measurement and control for energy conservation, it's good to understand how the different technologies work, where they're best utilized, because as we get into some specific applications, some technologies work better than others. So we'll talk about that. A little bit about Ebtron and why are we different. I'm not going to get into a lot of detail about that, but a little bit, and then the conclusion. So the first question comes up, why are we ventilating buildings and conditioning air in the first place? And, some of you folks out there probably use ChatGPT. I don't yet, so I just use Google. And it says, why are we ventilating buildings and conditioning air, right? And, it states here, I don't want to read everything that's on every slide. I'm not going to do that.
Mike, sorry to interrupt, but
Yeah.
you advance the slide so people can.
Do you see it says, why do we ventilate? Are you there? No,
No.
it's not work. Like my slides aren't advancing at all. Man, okay.
It's just on
Does
my
that
end.
work? Does that work? Did that change it?
That's working. Yep.
Okay, I'm going to have to do it this way. So, okay.
All right. Thank you.
Yeah, no, thanks for letting me know. Appreciate that. Okay. So, there's the agenda I just reviewed, right? So then we started out talking about, why do we ventilate buildings and condition air? As it states here, the process of ventilation, the whole concept between that and conditioning air is to help prevent buildup of indoor pollutants, reduce the risk of illness, indoor air quality issues, improve overall well-being. It started out a couple hundred years ago being primarily for body odors. How do we eliminate body odors in a hospital and provide ventilation so to reduce the smells, within a hospital space? Also, it states here, general purpose of ventilation, diluting the pollutants originating in the building and removing the pollutants from that. And pollutants can come from a lot of different directions. We can talk about that, a lot of different areas, as we'll mention. And then because of that, because it's been recognized that, hey, this is important for indoor air quality and occupant health and well-being, that we ventilate spaces and condition air, there are codes and standards that engineers are designing to that specify the amount of CFM per person in a space based on how that space is being used. And you may be using various, codes like the UMC, IMC. You may be designing to an ASHRAE 62 standard, an ASHRAE 170 standard if you're in healthcare. So there are standards and codes assigned, specifically because it's been recognized that this is important to, condition the space and dilute the pollutants. So it's all about the people in the buildings. That's why we're ventilating buildings and conditioning the air. And as it states here, more is not always better. More ventilation isn't always better. Now, at our factory in South Carolina, we overventilate on purpose. And, there's a cost associated with that, of course. You bring in more outside air, it has to be treated. And we're going to talk about that. But a lot of times it's really not the issue of whether or not somebody's ventilating their building. It's how well they're controlling the ventilation. Most buildings have ventilation designed into them. They're bringing in outside air, recirculating air. So it's not a function maybe of we're ventilating or not ventilating, but most buildings are actually over-ventilated. There's some that are under-ventilated, and we're going to talk about what happens with those two different circumstances. But most buildings are over-ventilated. And the assumption of more is better leads to some different issues, such as energy waste to condition excess air. Imbalanced airflow can cause indoor air quality issues, pressurization issues, especially if it's a negatively pressurized building. We'll show you some information on that. And then, compromised building health from the moisture buildup, infiltration, mechanical strain, allowing dirty air into the building that's not been filtered, not been treated, humid air coming into the building, those types of things. So it's really a function of controlling it. And our tagline is you can't manage what you don't measure, right? And you'll see that a lot through the Ebtron information. So how much does it cost to treat outside air? And people have asked me this question, and the answer, I don't know specifically for everybody's location what that cost is because of different kilowatt cost. Are you in a hot, humid, cold, humid, hot, dry environment? What's your environment? But if you type it into Google and you say, hey, how much does it cost? It states, roughly $5 to $8 per CFM per year to condition outside air. Okay. We know outside air is required to meet code. So without effective measurement and control of the outside air, it's very possible in most cases that there's excess outside air that has to be treated. And the key is to control that outside air. Why? Basically because of the cost. If you imagine a 100,000 CFM air handling unit, which is not that uncommon, and the engineer designed it with 10% outside air for proper, ventilation, dilution ventilation, as well as pressurization of the building. If that 10% is off by 50%, so you've got 10,000 CFM of outside air and you're off by 50%, you're bringing in 15,000 CFM of outside air, that could potentially cost $40,000 per year. Based on, $8 a CFM and 8,000 hours a year. Okay, so it might be an extreme case, but it's possible that if that unit's running 24/7, that could be the case. Now, if you're off by 50% in the opposite direction and you're only bringing in 5,000 CFM of outside air, now you've got indoor air quality and building pressurization issues. And then I use this example for things like air terminal units, small VAV boxes. Maybe it's a 25 CFM air terminal unit and it's off by 50%. So you're bringing, you're pumping 32.5 CFM into a room. That could potentially cost you $200 a year. And you might be thinking, okay, $200 a year is not an extreme amount of money. However, in a lot of high-rise buildings, there's not just one, air terminal unit VAV box. There's hundreds. So you take all the number of air terminal units you have, multiply times $200 per year, and you could see that could be driving, quite a bit of cost in your HVAC system. So as it states there at the bottom, overventilation really is the number one factor driving the higher, driving higher than needed costs with that HVAC system. So when we talk about ventilation and indoor air quality and how they go together, ventilation is required for code compliance. We know that. We know that dilution ventilation is needed for indoor air quality. Conditioned air is needed for the occupants, right? We don't want hot, stuffy, humid air. We don't want freezing cold occupants in the wintertime. We know that overventilation is expensive, as we just talked about. Underventilation affects indoor air quality. So managing and controlling airflow through an HVAC system increases your indoor air quality and reduces your energy consumption. Okay, it's not an either or, and I'll talk about that in another slide, but it's not really an either or situation. It's how do we do both? How do we, improve the indoor air quality and reduce energy consumption at the same time? So there's a lot of factors that influence overventilation. I'm not going to go into every one of these blocks that are on here. We'll provide a copy of the presentation in a PDF format afterwards. But there are a lot of factors that influence overventilation, and I'm going to cover those really quick. One of those has to do with say you have a fixed minimum position intake damper, you're not using any kind of airflow measurement. A test and balance guy came in and said, okay, at this damper position, we're bringing in a certain amount of outside air. And, that's all great when the air handler is running at 100%. What I can't do with the slide right now because I'm showing it in slides and not as the presentation. But if I clicked on this slide again, it shows the fan in high speed and then it shows the fan slowing down. So what happens is if you go into a night setback mode or you want to go into just, a lower flow from your air handling unit, when you slow down the fan, that changes the pressure in your mixing section. And when that static pressure in your mixing box changes, that'll have an effect on your outside air intake. You may not be bringing in as much outside air as you think you are because of that mixed plenum pressure change. And it doesn't take much. 1/4 to 1/2 inch of water column can be affected by massive percentages. And so it's very important to be able to control those dampers based on the flow, not based on the mixed plenum pressure. The second thing that can affect it, we talked it's in the upper slides, but this talks about damper hysteresis. And all I'm going to talk about on this one real quick, just in the essence of time, is dampers don't always go back to the same position every single time when you open them and close them. And this shows a study that we did at our factory where we opened and closed the damper multiple times, measured the position, measured the airflow at each position, and you can see there's a scatter. So the damper doesn't always go back to the same position every single time. You really want to control the damper based on the airflow through the damper, not the position of the damper itself, in order to overcome that. So damper hysteresis can affect airflow through your HVAC system. Another effect we talk about is wind effect. If there's a crosswind, it creates a negative pressure on your outside air intake of your air handling unit. It doesn't mean you're not bringing air in. It just means you may not be bringing in as much as you thought you were if you're not measuring and controlling. So a crosswind can create a negative pressure, and a direct wind on your outside air intake is going to create a little positive pressure. So that means you may be bringing in more outside air than you thought you were bringing in if you're not measuring that airflow and then controlling the dampers based on airflow. So again, you could end up with a indoor air quality issue or a over pressurization issue, where then you're treating unneeded air, if that makes sense. And another effect is stack effect, and especially up in the Northeast, high-rise buildings, you're going to see a lot of stack effect in the wintertime. The whistling up the elevator shaft, that type of thing. And what we're talking about here is not necessarily how this affects your return duct, which it does, and we can talk about that and ways to mitigate that. But if your return pressure changes, like you've got a recirculating system with a common return, and the plenum pressure in your return plenum changes based on what time of year it is, the density of the air, that's going to have an effect on your outside air intake. So that's, again, a reason to measure and control, and also measure and control return air, not just outside air. So what if I don't directly measure my airflow and I don't control that? Our little statement there, you wouldn't attempt to maintain temperature without a thermostat. You really shouldn't try to maintain your airflow rates through your air handling unit without some type of measurement device, and then controlling your dampers, because you could potentially be off by 50% because of all these different variations we talked about. There are some, back in the day, people, before there were direct airflow measurement devices such as we have now, there were different ways to calculate it. So there was a delta CFM method where I would calculate my supply air, calculate my return air, do the math, and say, okay, I know I have so much outside air coming in because it's a difference between my supply air and my return air. That's not always the most accurate way of measuring it. Just like adiabatic mixing methods, differential pressure methods, those type of calculations, you can be off by 25% or more in your calculations. And we have other presentations where we can actually show you the math for each one of those situations and why that may not work as well as some people think it does. Okay, so if you don't directly measure, you could potentially be off by 50% on your outside air intake. Really quick, I'm going to cover one other issue here. ASHRAE standard 241 is a standard that recently came out. It's built on top of the the IAQ procedure for the ASHRAE 62.1. Talks about a building readiness plan in case there's another infection risk management mode, another pandemic type of event. And my point here is there are technologies out there. Buckley represents several technologies to help purify the air, clean the air, do different things to help with indoor air quality. And that's great. I got nothing against any of those products. I think it's great to utilize whatever resources are out there to try to provide the best indoor air quality you can possibly provide. But what the standard says is that if you're utilizing those devices, you can actually reduce the amount of outside air you're bringing in pandemic mode or in IRMM mode. And so as an engineer, if you're designing a system and you're going to reduce the amount of outside air during the pandemic mode based on these cleaning procedures, I think it becomes more pertinent than ever to measure those airflow rates, because if you're off by a little bit, it can have a huge effect on your indoor air quality. So we work very well together with those types of technologies to ensure that you are providing the best indoor air quality possible, but also you're not reducing your outside air intake, your dilution ventilation rates below ASHRAE standards. So it's very important to measure those rates to ensure that you don't drop below those ASHRAE standards. So the conclusion of this section is, hey, there's a lot of things that can affect your airflow rates in outside air, return air, supply air, other areas in the HVAC system. So it's very important to measure those rates and then control those airflow rates, control the dampers based on the measured airflow rates. So then the question comes up, how do I measure airflow rates, right? So Mike, you've talked about here's why we're doing it, here's the need for it, here's some factors that affect it. And you're telling me I need to measure and control, and that's great. I understand. How am I going to do that? How do I really measure my airflow rates? And there's different ways of doing it. Like I mentioned, back before there were some direct methods for measuring, outside air and supply air, return air, different things like that. There were the calculated delta CFM methods, temperature mixing methods, pressure differential methods. Those were used, but they are not as accurate as a direct airflow measurement device. You could be off again, as I mentioned earlier, 25 to 50% on your calculations. There's differential pressure products that came out, and companies are using differential pressure products, piezo ports, piezo rings, to try and determine, velocities and CFMs through a certain space. We'll talk about that. In some limited applications, there's companies that are utilizing a vortex shedding device for measuring airflow. Those have their applications. We'll talk about that. And then the third way of direct measurement is thermal dispersion. Okay, is a very popular method for measuring velocity and volume. Okay, so there's basically three of those three methods of direct airflow measurement. In doing a comparison of those different technologies, what this shows is every device has a place. Hey, I'm flying back and forth, throughout my territory all the time. I'm hopping on the Delta Air, the Delta jets, flying at 500 miles an hour. That's 40,000 feet per minute. Airplanes use pitot ports to measure the velocity of the airplane. Right? Differential pressure devices are great at those high velocities. Everything has its place. In HVAC, we're typically dealing in lower velocities, what I consider to be relatively low velocity applications. A lot of our designs are 100 to 600 feet per minute velocity. Typical air handling units, you're going to see max velocities across a chill water coil, across a DX coil, of 500 feet per minute. Why is that? Because if you go any faster, if you go across that coil at a higher velocity than 500 feet per minute, you have potential of spitting moisture, water off the coil downstream into the system, and you don't want moisture in your ducting system because it creates mold and mildew. So you reduce the velocity across your chill water coil to prevent that from happening. I've seen filter specs up to 625 feet per minute, but as low as 350 feet per minute across a filter. So we're dealing in relatively low velocities. The challenge is that with differential pressure, that product becomes less sensitive in the lower velocities. The turn down on a differential pressure device is actually a square root relationship. So if you're at plus or minus 20 feet per minute, you could be, in a 4-to-1 turn down, your plus or minus could be 320 feet per minute. And so, how do you control a airflow measure, an HVAC system, with such a big scatter on your velocity? So that's one of the challenges with differential pressure. There's other challenges as well, but they become less sensitive in the lower velocities, less accurate in the lower velocities. Vortex shedding has an issue where it actually drops off below 370 feet per minute, about 370. And the reason why is you have a vortex shedding device, it's shedding these small vortices. The lower the velocity, the smaller the vortice off that. And there's a reading device that reads the vortices. And at some point, it cannot read such a small, vortice anymore. And it's about 370 feet per minute. So if you're using an averaging vortex shedding device and one of the sensing nodes drops below 370 feet per minute, it's actually going to read 0. And that's not an effective average, right? Thermal dispersion by design actually becomes more sensitive in the lower velocities. So as that heat disperses off that thermistor, whatever kind of thermistor is being used, the lower the velocity, the easier it is to measure the heat differential and measure the current change in the thermistor. That makes it more sensitive at the lower velocities. So if you're going into turn down modes, you're going into night setback modes, you're trying to do precision control of a VAV box, of a air terminal unit, and you want to turn it down into a really low volume, low velocity, you're better off with a thermal dispersion device than with those other devices. The ASHRAE handbook itself states that differential pressure really shouldn't be used below 600 feet per minute. They show there 600 to 10,000. The other issue is typically differential pressure is a percentage of full scale device. So when you get in, as we mentioned before, the 4-to-1 turn down and being a square root relationship, so the error increases by that factor, they are not as accurate in those lower flows. Thermal dispersion, it shows here 20 to 10,000 feet per minute. We can actually read 0 flow, but that's we'll talk about that some other time. And it is a percentage of reading device. And so any inaccuracy with thermal dispersion at maximum is the same percentage at minimum. So if I'm at 2,000 feet per minute plus or minus 3%, then at 100 feet per minute, I'm still plus or minus 3%. So very accurate at the lower flows. This slide here shows the various differential pressure devices that are utilized in order to try to measure airflow. Just a couple of quick things, like the cross flow ring in an air terminal unit. If you're really trying to lower your airflow through that air terminal unit, that's not as accurate of a way to do it. A lot of the units require flow straightening devices. There's one of the units where they actually increase the velocity of the air on purpose in order to try to get a more accurate measurement, because they understand that the lower velocities it's not as accurate in the lower velocities. So those are some, various differential pressure devices that are being used. From a thermal dispersion, there's several different thermal dispersion technologies that are utilized out there. All thermal dispersion is not the same. You'll see Ebtron in the middle. You're going to see a couple other brands on there that utilize a chip thermistor as opposed to what we use in the bead and glass thermistor, and I'm going to show you a comparison of that. All thermal dispersion is not the same. Chip thermistors are mass produced. They're not individually tested and calibrated, such as the bead and glass thermistors. They're sensitive to installation effects. One of the brands uses an externally heated chip thermistor, which then adds a third, a separate variable to the algorithm to calculate the flow. So that can cause some issues. And then there's a jacket over the chip thermistor that affects sensitivity and responsiveness. So if you have dynamic changes in your airflow system, it may not recognize those dynamic changes fast enough to adjust your airflow system. So responsiveness is very critical. Although they're typically better than differential pressure in most applications, chip thermistors are not the same, quality, accuracy, repeatability of something like a bead and glass design. So in conclusion of the technology comparison, we're dealing in relatively low velocities, as I mentioned, right? Outside air intakes, induct applications. Fan inlets are a little higher in the velocity. We have a solution for that, but it's still relatively low compared to a lot of other things. Differential pressure, they have their place, just not as effective in low velocity applications as we talked about. Chip thermistors are not the same as a bead and glass thermistor. Okay, so that information there. So what I want to do really quick is I got just a couple of short slides. I don't want to make this an Ebtron commercial. I just want to show you the different ways of doing things. And, it is going to be a little bit of an Ebtron commercial though. So this shows, who is Ebtron and why are we different, right? Advanced thermal dispersion technology. So the company's been in business 1983, 42 years. We pioneered outdoor airflow measurement back in 1989, with our technology. And so we've been doing that for a really long time. Last check earlier in the year, we had, I'll show you our sensing node. We had manufactured some 3.5 million sensing nodes. We're probably getting close to 4 million now. And, that's a lot of airflow measurement stations in the last 35 years. And again, our technology is the advanced thermal dispersion airflow measurement. This is our facility down in South Carolina. We have a new building in the upper right-hand corner there. There's actually another building that we built there, but this is where we do all of our manufacturing. We actually do all of our own printed circuit boards, all of our hand assembly of the sensing nodes, the probes, the calibration of the products. Everything is done in-house at our facility in South Carolina. We're American-owned, American-operated, try to use, as many components as we can get, locally, but obviously there's some components you have to get from, other parts. So since I'm not in my presentation mode like I'd like to be, this slide gets a little cumbersome, but the heart of Ebtron is this thing called a bead glass thermistor. Okay, it's the sensing node that utilizes the bead glass thermistors. And can you guys see my picture, Dean? Do you actually see me?
We can see the slide, yeah, and we can see your camera.
Okay, so I'm holding up the sensing node here to my camera. I don't know, can you see that, Dean?
A little bit. It's
okay.
difficult.
It's difficult. Okay, anyway, so that's our sensing node, right? So the whole idea of the sensing node is we did not invent the bead glass thermistor, okay? What we figured out is how to utilize it for airflow measurement. So we take two bead glass thermistors, we put them in a sensing node. We heat one of the thermistors to a certain level. We put current through it. As air flows through that sensing node, heat dissipates off that heated thermistor, thermal dispersion, right? As that heat dissipates off that that heated thermistor, the current changes in that thermistor. The current that we're supplying to that thermistor changes. We know what that current is because we're the ones who are providing it. We know what the temperature difference is between the two bead glass thermistors, and therefore we can calculate velocity or mass velocity. Now, these bead glass thermistors are like 0.01 degree Fahrenheit temperature sensing devices. So that's crucial to know for various reasons, and I'll show you some later on. But that, we're doing that temperature measurement between those two thermistors and the power in order to calculate the velocity. So it's a very, very accurate way of calculating the velocity through that sensing node. Once you know how many sensing nodes you have and the area of the duct that you're providing it to, you can calculate your volume, right? Your velocity times your square foot is going to give you the volumes. How many CFM do I have flowing through that space? So it's a very accurate way of measuring your CFM. The thermistors are oven aged for stability, hermetically sealed for long life, designed to survive extreme temperatures. Each one of those sensing nodes is individually calibrated at the factory. And I'm going to show you one more slide on that, and that's it. They are potted with an advanced epoxy to ensure that the thermistors are protected from any kind of outside elements like salt water, moisture, things like that. So this is a slide that just covers the calibration really quick. These are calibrated. We put them through controlled temperature baths. We put them through wind tunnels where we calibrate them at 16 different flows from no flow up to 5,000 feet per minute for our duct mounted units. We calibrate up to 10,000 feet per minute for our fan inlet units because the velocity profile through a fan is a little different than you would have through a duct. And all of these are individually calibrated and barcoded. Every single one of them has a barcode and can be traced back to the original calibration. And we utilize company, industry, I guess a government agency down in the DC area called the National Institutes of Standards and Technology. And they actually calibrate do a calibration with it's laser Doppler anemometer. They do a calibration. They send us the data, and we use their data in order to calibrate our sensing nodes. So it is a NIST traceable standard, every single sensing node back to the original NIST standard. Nobody else in the industry can provide that much data on their calibration as we do. So the key here is they do not have to be recalibrated in the field. There is no drift associated with the sensing nodes. They don't drift over time. So 10 years from now, that sensing node is going to perform the same way it did today. So there's no change in that performance. So that is the heart of what is Ebtron, the bead and glass thermistor technology utilized in the sensing node. And I wanted to cover that because the next thing we're going to get into, and I see it's 20 minutes to go till 1 here, is really quickly we're going to talk about how do you implement this to reduce energy consumption. And a lot of it has to do with, looks like all my hidden slides aren't going to be hidden, so I got to rush to cover some. Anyway, a lot of it has to do with fine control over your airflow systems in operation, okay? And you got to have a device that can really measure the low flows in order to provide that kind of control. So methods for decreasing energy usage and maintaining indoor air quality. There's 5 basic methods, and then the number 6, airflow monitoring feedback, is great for owners, operators, people that are managing the system after it's been installed. And it's really not an either or option between indoor air quality and energy usage. It's both. You can reduce energy consumption and maintain indoor air quality at the same time. So really quickly with demand control ventilation systems, if you're designing DCV applications for education facilities and places like that, it's using a rate-based occupancy level in order to measure and control airflow rates. And by doing that, you don't overventilate. Very simply put, right? The challenge with demand control ventilation is a lot of the demand control ventilation designs are based on a CO2 measurement, and CO2 is really a proxy for population count, and so you may not have an accurate population count of the space. There's some other issues as well. If you design it to ASHRAE 62.1, is that in the very beginning, you're not ventilating. You could be potentially underventilating as people enter a space, as there's a group of people in a conference room, a lecture hall, somewhere like that. In the beginning, until your CO2 level rises between 400 ppm and 1,000 ppm, you may be underventilating that space. And then you're ventilating the space, and there's some other issues related to, accuracies and things like that. But then at the end, you could be potentially overventilating the space because there's no max limit on your ventilation rate. As long as your CO2 level continues to rise or stays above 1,000, it's going to continue to increase the ventilation. But then also, once everybody gets up and leaves, you're still ventilating an empty space. So that's a waste of energy. So our goal is to assist our customers with design strategies, control strategies to help DCV applications work better. Okay, it's not that we want to eliminate CO2 measurement for DCV. We don't believe it's the best way to go about it, but that's not the issue. We want to help our customers design better systems. So this is a control strategy, very simple right here, where you put a minimum on your outside airflow and a maximum. So you're never underventilating in the very beginning, and you're not overventilating at the very end, but you're still meeting ASHRAE 62.1 guidelines for DCV ventilation. So that's a really quick review. We have a 1-hour presentation, 2-hour presentations just on demand control ventilation. We can provide you on, at another date. But that's just a really quick overview of a way to reduce energy consumption, but still maintain air, indoor air quality, utilizing this with DCV. Economizer strategies. A lot of engineers obviously are designing air handling units with economizers. You want to use free cooling in order to reduce energy consumption. The challenge is, are you utilizing free cooling at the right time? Because if you're not, you could be introducing untreated air into the system, humid air into the system. There can be some factors associated with that. So the key is, as we're showing you here, as I mentioned earlier with Ebtron, we're doing a temperature and velocity measurement at every single sensing node. So we can measure when there are stratification issues, weird velocity profiles through your duct, things like that. If you use an averaging temperature sensor in a duct, that may not take into account, probably not, any kind of stratification or velocity profiles. Utilizing the temperature output from the Ebtron, you're actually able to measure velocity profiles and stratification within a duct, and we provide a weighted temperature output from our transmitter. So if you set up your averaging sensor to go into economizer mode at 75 degrees, your weighted average in this example is actually 76.7. You would not want to be in economizing mode. Okay. Now, the opposite could also be true. You could have 2,500 CFM at 80 degrees and 5,000 CFM at 70 degrees. And then what would your average temperature be? Your weighted average would be maybe 73.4. So you might be in economizing mode. So it gives you better control over your economizer strategy to ensure that you're operating the most efficiently and as well not introducing untreated air into the system, which then can cause indoor air quality issues. We can also provide a humidity sensor into the system, and I'm not going to go into a lot of detail on the humidity sensor. The calculation we use, I'll share this with you, is it's a patented algorithm that we submitted and got a patent on how to utilize the humidity sensor along with the temperature outputs of every single sensing node in the system to provide a velocity weighted enthalpy example. So if you're designing air handling units with economizers based on an enthalpy calculation, this is going to give you a more accurate enthalpy output, a more accurate enthalpy calculation, again, to ensure that you're economizing when you should be and not when you shouldn't be. So again, it helps with energy efficiency, but it also helps with your indoor air quality. So utilizing measurement and control, again, for airflow affects pressurization of buildings, okay? Proper pressurization of the building prevents unfiltered, unconditioned air from infiltrating the building. Every time somebody opens a door, opens a window, maybe there's cracks in the walls or ways that air can leak through the building. And if you have a negatively pressurized building, these types of things can enter the building without being treated. And that's going to cause indoor air quality issues, moisture, different things like that, right? So utilizing airflow measurement and control is necessary to make sure that you number one, adjust to dynamic changes. Also, pressurization changes outside, barometric pressure changes, changes within the building, right? To reduce energy consumption and, improve your indoor air quality. So a quick picture to show what we're talking about here is it's really a function of mechanical ins versus mechanical outs. A lot of engineers tell me they design with a 10% in versus out to maintain proper building pressurization. If you're overly positive, say you're bringing in 20% outside air versus that 10%, you have to treat that excess outside air. That costs money. However, if you're set up a 100,000 CFM system, like I mentioned earlier, and you're only, bringing in 5,000 CFM of outside air, you could potentially have a negatively pressurized building, which then causes indoor air quality issues. So the key is to measure and control your flow rate so that you maintain the right amount of pressurization, not too much, but not too little. And that improves your energy consumption and indoor air quality. It's a pretty simple system. On a more micro level, if you're looking at specific room applications, pressurization of a lab, well, if you have supply air and return air, and you have air terminal units, and you can precisely control the amount of air through those air terminal units, you can control the pressurization of that building, of that room. With a lab, you want to be negatively pressured, but how much negative pressure do you want? How do you control that? And by utilizing, our type of technology, you can precisely control your VAV boxes, air terminal units, better than other types of technologies for maintaining that proper pressurization. Hospital applications, again, you're designing to ASHRAE 170. You have to have so many room changes per hour. How are you measuring that to make sure you have the proper number of room changes, as well as proper pressurization to ensure that infections don't get into rooms, don't leave rooms, those types of things. And so by measuring and controlling at your, again, VAV boxes, air terminal units, you can measure and know how many, room changes you have, and you can maintain your proper pressurization. And again, it talks about in a lot of these slides, it's, how, it's good for turn down applications for precise control. And, that's where thermal dispersion shines. Variable airflow systems, there's a couple ways of doing this, right? You're adjusting the airflow rate based on, the temperature requirements, occupancy levels in each zone. Thermal dispersion is more accurate and responsive at the lower velocities, as we talked about before. Again, going back to the air handling unit, if you go into a night setback mode, you go into a turn down mode, how do you ensure that you're providing the right amount of outside air, through that system if you're not measuring and controlling during those low flow applications? Okay, so it's important to have the proper kind of measurement and control during night setback, during turn down modes. On a micro level, looking again at things like air terminal units we talked about with the hospital or the lab applications. Right here shows a picture of an air terminal unit, right? And if Buckley sells the Price product, you can integrate Ebtron with a Price. They know how to do it. You can talk to Dean about that, or anybody from Buckley. And you can utilize our Ebtron, what we call the ELF unit, with an air terminal unit to give you precise control over that damper so that you're not over ventilating a space. Again, more accuracy at turn down requirements, right? Enhanced DCV control, DOAS zone control, potential energy savings, and all those applications. Typically, you put your airflow measurement device, before your modulating damper, not after. There's a lot of reasons for that. We can talk about if you need. The one area where you actually can put it after is like we're showing here, a hot water reheat coil, which I've seen a lot of those up in your neck of the woods. You can actually put an airflow measurement after a hot water reheat coil because it acts as a flow straightener, and you get more laminar flow after that. But typically you don't want to put it after a modulating damper because your velocity profiles are crazy and it's almost impossible to accurately measure. DOAS zone control, if you're utilizing a lot of DOAS systems and you're supplying multiple zones, how are you controlling the flow rate through each of those zones to ensure that every zone is getting the right amount of air? And that if it's uncontrolled, air follows the path of least resistance. It's going to flood the first room with everything, and the guy at the end of the hall is not going to get anything, right? So it's important to be able to have control in each of those zones for proper pressurization, for zone control, those types of things. For balancing, balancing flow, it's similar to what I just talked about with the DOAS zone control. Right? Proper balancing helps avoid excessive airflow, proper pressurization, prevent infiltration, again, indoor air quality and reduction of energy. They go hand in hand. This shows an example if you're doing VRF systems and you have a common exhaust, maybe you're using an energy recovery unit to supply some supply air, some makeup air to each of those spaces, right? And how are you measuring and controlling those airflow rates into each space? So it's very important to have the proper kind of measurement and control. Also, as I'll mention really quick here with the energy recovery unit, you can actually measure your exhaust and outside air on an energy recovery unit to make sure you have the proper balance through your energy recovery unit. Because if you don't have the proper balance of exhaust air and outside air, whether it's a plate exchanger or a heat wheel, they may not operate most efficiently if the balance is more than, say, 50% off. For zone control, this is a solution that we have. It's a high quality damper with an airflow measurement device combined. This is great if you're using a common return duct in a large high rise, other types of locations, but this is a great solution for zoning. So monitoring and feedback, again, this speaks a lot to the owners, the people that are operating the buildings, because once you have the building, it's been commissioned, it's been turned over, how do you make sure that the HVAC system is working at peak performance, that you don't have issues like broken belts, collapsed filters, clogged coils, everything like that? Well, if you can monitor and measure airflow rates, temperature rates, things like that through your HVAC system after the fact, it helps you operate your building more efficiently. So it says here, what can we measure and monitor? I'm going to provide all this data to you, but here's the different things that we can measure and monitor with our systems. The benefits, this is on our website, and I'm going to provide this to you as well. But from an owner perspective, you're verifying that your dampers are working properly. You're verifying that your belts haven't broken on your fans, that your coils aren't clogged, that your filters haven't collapsed, that you have proper pressurization, your energy recovery ventilators are working properly. We do a lot of work in data centers on, data center cooling and hot aisle, cold aisle containment, different things like that. So there's a lot of benefits to measuring, the airflow rates in all these different, locations, precise measurement. All right. So I'm going to skip over. I got to skip over some stuff here. This is a device. We have a Bluetooth connectivity onto the transmitter where you can actually download an app on your phone, be able to connect to a Gold Series transmitter from Ebtron and monitor everything going on with that airflow measurement station. We have a new product that we've launched recently, the SDX 1000. This allows us to integrate up to 20 airflow measurement devices, airflow measurement stations into one touchscreen device. So 20 Gold Series transmitters tied into one device. There's a discussion on how to do that. If you're interested, we can share that information with you. But it's great for a mechanical room management system. If you have multiple air handlers in a mechanical room and multiple airflow measurement stations in each air handler, you can tie all those back into one touchscreen device and be able to see what's going on with all of those airflow measurement stations at one station, at one location, without having to go back to the BAS system and try to pull all that data out of the BAS system. And if you're using analog outputs to connect to the BAS system, a lot of that data is not going to be available anyway. It's only available if you're using Ethernet or BACnet or something like that. So this is a great way to get all that information at one central location. We have apps that are included with it, and if you have an idea of a custom app that you would like us to write for you and include in the touchscreen device, we can do that as well. So we can talk to you about that. If you have an app you want specific to your company, your location, something like that. So I have to skip over a bunch of these slides that I didn't want to, you wouldn't see if I had the normal presentation. So anyway, real quick to wrap things up, because we're almost done here. So what are the advantages to utilizing Ebtron for airflow measurement and control? It's more accurate than other types of technologies for airflow, temperature, humidity, enthalpy. It's better during, turn down capabilities, as we discussed, more sensitive in the lower flows. Better long-term stability. There's no drift in the sensing nodes. And so you don't have to go back and recalibrate, bring your test and balance people back in once a year and do another report and update all your data. It's not required. We have an airflow station for every application and price point. Don't think that, hey, they're too expensive because all I ever see is the Gold Series products. In your smaller locations, smaller applications, we have all kinds of different products. And, Buckley's fully aware they can help you with any application that you have. And then we have the best support in the industry. When you call the factory, you get human beings to help you on the phone. We have great, representative network. Buckley's a phenomenal representative for us. They've been a representative for us for, I don't even know, 30 some years. And they do a phenomenal job for us. So in conclusion, hey, you need to bring in outside air to ensure code compliance, improve, occupant well-being, maximize facility performance, and increase energy efficiency. You want to measure the outside air and return air supply or economizer to ensure code compliance, and facility performance, energy efficiency. And then the key is specify Ebtron to provide the highest level of accuracy for airflow measurement in multiple applications, not just outside air, but all different air handling unit locations, point of view, such as induct, fan coils, VAV boxes, even chill beams, different things like that, right? So again, our tagline, you can't manage what you don't measure. So it's 1 o'clock, and thank you very much. We can, if anybody wants to hang out and ask a few questions, we're more than happy to have that. And if you got to go, then I can understand for those that have to leave.